We are now on chapter 20, which is about electric circuits. All of you know we need electrical energy to operate any electrical device or appliances, whatever you use daily at home. Uh, we can use the battery as the source of electrical energy to operate appliances. In a battery, chemical reaction takes place where the electron transfer from positive terminal to the negative terminal. The symbol you see in this picture here represents positive and negative terminals of a battery. There is always a potential difference which exists between positive and negative charges on battery terminals. Now we can define the maximum potential difference that exists between the terminals of a battery as electromotive force, and to define the current we can always measure the flow of charge from one end to the other end, rather from one terminal to the other terminal, which is electric current. You can refer to figure 20.2 and 20.3 on page 542, and also go over the example on page 542, which is example 1. Current flow is similar to water flow in a pipe. If the pressure is more in a pipe, there will be more water which will be flowing from one end to the other end of the pipe. It depends on the pressure of the pump, which is used to expel water in a pipe. Current I is directly proportional to the voltage. You get more current if the voltage is high, and vice versa is true. If voltage is less, the current will be less. There is always a resistance, which is defined as the ratio of voltage applied across a piece of material to the current I through a material. So R we can define as V over I, or V equals I times R. We define this as a Ohm's law, where R is constant and the resistance of a piece of material is R, where the unit of R is in ohms. The symbol is this. Now let's define what is resistivity. Let's say there is a wide range of material we take from different length. Let's say 1 meter to 2 meter, 3 meter and 5 meter. We can represent that as an L. And a cross-sectional area of A, we have an equation now as you see, R equals rho times L over A. This rho is constant, which is known as the resistivity of the material. This is in a table 1 where different materials have different resistivity. And the unit for resistivity is ohms times meter, which is rho ohms times meter, as you see here. Go over example 3 on page 545. Then we go to the next topic now, which is electric power. As you know, we always say so many wattage of the bulb, or so many wattage you get as in any appliances you use. So we can define P as the electric power, charge in energy divided by time, rather how much charge flows over a period of time. So Q times V, or delta Q times V over delta T, will give you P. Now look at this. You have delta Q over delta T, which is defined to be the current, rather the flow of charge over a period of time. So P will be ultimately I times V. This is an important topic now which I am going to speak, which is alternating current. In house and in commercial use, we use alternating current. No batteries, unless you have small appliances, you can always use battery, but most of the time we have alternating current, where the current is defined to alternate its polarity, or the voltage changes from negative to positive. As you see, this is a sine curve with time. Let's say this is one period starting from 0. It goes to voltage positive maximum, then come back to 0, then going to negative max, coming back to 0 over a period of time. So starting from 0 to this point is one period or one cycle. So voltage is produced between terminals of a generator. The sign of generator is this, as you see here, which is alternating current. At each movement of the time, V equals V0 sine 2 pi ft. V is the current you want to measure, or the voltage you want to measure at a time t, will be determined by V equals V0 times sine 2 pi ft, where f is the frequency, t is the time. So V0 is the maximum voltage, as you see in this graph here. F is the frequency, t is the time. Anytime, anywhere in the graph you want to find out the voltage, from there you can always calculate the current depending on the power. Now refer to the figure you have, excuse me, 2011 on page 555, where I equals V0 over R times sine 2 pi ft, where I equals I0 sine 2 pi ft. Same thing again here. This is your initial current. This is the current you want to find out, which is I at a time interval t. So you have frequency, which is f, t is the time. So finally you have this equation here, I0 equals V0 over R. We define power in AC circuit like we define power in regular battery terminal, or the battery which is a direct current. So power here is a vector quantity which equals I0 V0 sine 2 pi ft. Earlier we defined power as V times I. Now we have sine 2 pi ft because of the alternating current. Now P equals half I0 V0, that you see in the graph here in your book. So P will be I0 under root 2 V0 divided by root 2, which is defined to be IRMS. RMS means root mean square. So IRMS will be equal to I0, which is your initial current, divided by root 2. VRMS will be V0 divided by root 2. Go over the example 6 in page 551. We use in daily use two different type of wiring. One is known as series wiring, other one is parallel wiring. We have different resistors here, this you see, like R1 and R2, and a source of supply is a battery here. Look for the figure you have, 20.14, page 552. Here the flow of current in resistor 1 and resistor 2 is same. So the resistors are connected in series so that the electric current passes through each resistor is the same. So you have whatever the current, let's say you have voltage 6 here and you get 1.2 amps here, then you will have 1.2 amps here, but the voltage will be different across R1 as well as across R2. Now you are supposed asked to find out the total resistor in the circuit here. So we'll add R1, R2, R3, R4, so on and so forth. All the ohms put together will give you the total resistor in the circuit. We have only two here, so R1 and R2. You can add them up to find out the total. Go over the example 9 in page 553. Here comes the parallel wiring. As you see the circuit here, R1 and R2 are connected in parallel. Here the current divides into two parts. One part goes through R2 here, other part of the current goes through R1, and you have voltage supplies from a battery, positive terminal, negative terminal. So as you look into this circuit here, previously in the series circuit, the current passes in resistor 1 and 2 are the same, but here the voltage, if you measure the voltage across R1, voltage across R2, they will be the same. Let us say the battery is 12 volts, then you will measure 12 volts in R2, 12 volts across R1, but the current will be different. So in parallel wiring, the voltage across the resistors are same, the current branches out. So let's say you start from here, from positive to negative, comes back to the negative here. So it branches out to I1, I2, two different parts depending on the value of the resistor. So in a parallel circuit, if you are asked to find out R total, that will be 1 over R parallel, or R total for parallel will be 1 over R1 plus 1 over R2 plus 1 over R3, so on and so forth.